Hi everybody. Well, in today's lecture we are going to learn a very fresh concept related to when two matrices are equal. Now before I move on to that concept, let me remind you that we already know that a matrix is known or is represented or is identified by two features. What are those two features? Well, if I am talking about a general matrix, what is or what are the two basic prerequisites which make a matrix complete? First of all, you should be aware about the order of the matrix, isn't it? The first thing you should be aware about is the order of the matrix. Why? Because the order of the matrix specifies all the specific positions which are there inside the matrix needed to be filled by the elements. Until and unless order is known, you don't know how many rows and how many columns are there, and hence how many intersections are there, and hence how many elements with what identifications would be sitting in that matrix. So order gives you all of that. It specifies all the several positions at which when the elements are going to sit is going to give you the entire complete matrix of that order with those elements, right? So order is required to give you the specific positions. Next thing is, at those positions what elements are going to sit is the next thing which determines a matrix. So you should be aware about the elements which sit in the position specified by the order, and it is these two things which basically make a matrix complete. If you want to write a matrix, you should know the order of that matrix and you should know the elements which are there sitting inside that matrix which are arranged. Okay? Once these two things are known, the entire matrix is there in front of you. Secondly, if suppose A is my matrix, let me just write it down like this. You can make square brackets, sometimes people make these simple brackets as well. Suppose I write 2, 7, 6, 1, 1, 0. Now this is a matrix of which order? You can see there are 2 rows and there are 3 columns, right? This is my row 1, this is row 2, this is column 1, this is column 2, and this is column 3. So 2 rows, 3 columns, you always write the number of rows first, number of columns next. So this is 2 cross 3. Is it understood? This is 2 cross 3. So this matrix is of order 2 cross 3 and that's matrix A. The moment it is of order 2 cross 3, it has 2 rows, 3 columns. That means how many intersections are there? Well, obviously 3 into 2 is 6. 6 elements are arranged inside this matrix. So 6 intersections have to be there. At each of those intersections, one of these 6 elements is sitting, and hence these 6 elements are arranged in this rectangular array form. The point is, what are the identifications of these elements? You can see that row 1 intersects with column 1 to produce this particular position. At this position sits the 1/1th element, and that 1/1th element is 2, whose name is A11. Similarly, row 1 intersects with column 2 to create this intersection point, which is the space to accommodate the 1/2th element, which is A12, and in this case that element is 7. Similarly, row 1 intersects with column 3 to create this intersection point, intersection space, to place the very 1/3th element, and that is A13, which in this case is 6. Similarly, row 2 intersects with column 1 to create this intersection point, which is the place to make the 2/1th element sit, and that is A21, and in which case this is 1. Similarly, row 2 intersects with column 2 to create this intersection space wherein the 2/2th element sits, whose name is A22, and here that is equal to 1. And similarly, the second row and column 3 intersect to create this intersection space wherein the 2/3th element of the matrix sits, whose name is A23, and that element here is 0. Okay? Why am I discussing this is, another way to represent the element sitting inside this matrix is what we need to know now. What is that alternative way which is going to be severely useful in our next lectures and sessions? So here what happens is, either you say that A11 is 2, either you say A11 is 2, or you can say matrix A's 1/1th element is 2. Either you can say A12 is 7, A12 is 7, or you can say matrix A's 1/2th element is 7. Either you can say A13 is 6, or you can say matrix A's 1/3th element is 6. Either you can say A21 is 1, or you can say matrix A's 2/1th element is 1. A22 is 1, or you can say matrix A's 2/2th element is 1. And similarly, this is A23 is 0, or matrix A's 2/3th element is 0. What basically I want you to note from here is that matrix A's ijth element is what is denoted by Aij. If A is a matrix of order m cross n, that means m rows, n columns, the first subscript I varies over the number of rows, j second subscript varies over the number of columns, and so I say that Aij is small aij for all I varying from 1 to m and j varying from 1 to n. This is the concept I want you to note very nicely, because in the further topics we would be using this notation that capital Aij can be replaced by small aij, or small aij can be replaced by capital Aij. Okay? If the name of the matrix is B, then it will be B matrice's ijth element. If the name of the matrix is capital C, then capital C's ijth element is Aij. Right? In any way, this is what I wanted to make you note. Once this is understood by us, let us move towards understanding of the concept of equality of matrices. Now see, when I am talking about two matrices being equal, obviously I cannot work with a single matrix and teach you the concept of equality. I need two matrices for that. So, when I am talking about the concept of equality of matrices, I need two matrices. When would you say that the two matrices are equal? Now see, whenever two things are equal, they exactly are same. They have no difference in them. They are equal. They are not similar looking or similar, but they are exactly identical, exactly equal, copies of each other. It's like photocopies of each other. That is what is the meaning of equality. So when I have one matrix and I have another matrix, what is the very condition which is going to make them equal? Just understand, just try to, I have not taught you any concept till now, but just try to understand. If I say that this is one matrix and I say this is another matrix, are these two matrices equal? Even when you don't know the concept of when to say two matrices are equal, you can very easily say that no, these two matrices are not equal. The rectangular arrangement over here is like this. A vertical rectangle is there, whereas over here the arrangement is in the form of a square. So how can these two matrices be equal? They are not identical looking. They are not looking like photocopies of each other. So definitely they are unequal to each other. Is it understood? So one thing is very much evident, that the look of the matrices is necessarily supposed to be same. They should look the same. So if I say this matrix, and suppose I say 2, 1, 7, 7, 6, 0. What about these two matrices? Well, of course, one thing is sure, that they are looking the same. The 6 elements arranged here in a rectangular array, that rectangular array is exactly the same in both these matrices. It's a vertical rectangle here with breadth 2 and length 3. The vertical rectangle is here with breadth 2, length 3. What do I mean by the look of these two matrices is the same? Look of these two matrices is the same means the rectangle has the same length and same breadth in both the matrices. Right? Length is the same, breadth is the same, means what? Breadth is denoted by the number of columns or the number of rows. This is if I say this is the length and this is the breadth, then the length is denoted by columns and breadth is denoted by rows. We know that. So if I am saying length and breadth is the same, then only the look of the triangle will be same. That means I am trying to say that the number of rows and number of columns in these two matrices is exactly the same. So, two matrices are going to be equal provided number of rows and number of columns in both the matrices is exactly the same. Because there is a concept, number of rows and number of columns are same in two matrices, that means the length and the breadth of the rectangle in which the elements have been arranged would be exactly the same. So, the two matrices would have a common look. If this is going to be a vertical rectangle, even this is going to be a vertical rectangle with the same length and same breadth. So, of course, I can in the first look try to talk about these two matrices being equal. Here what was happening was that the length and breadth was completely different. Here there are 3 rows, 2 columns, here there are 2 rows, 2 columns. So, length is different from the breadth. That means length and breadth are not same of these two matrices, and therefore, in the first look itself I can say that they are unequal to each other. Is it understood? So, the very first concept related to equality of matrices is what? When I talk about two matrices being equal, under the head equality of matrices, we say that let A be a matrix of order m cross n. So, A is Aij m cross n. So, A has m rows and A has n columns, and B be a matrix of order r cross s. So, B is a matrix of order r cross s, that means it has r rows and s columns. A and B are two matrices, then A is said to be equal to B provided what happens is, provided first point, what happens is that the two matrices should in the first look like alike. They should look alike. They should look alike. That means that rectangular arrangement should completely be the identical one. Okay. So, the rectangle here and the rectangle here should be the exact same rectangle. If it is a horizontal rectangle, even this should be a horizontal rectangle with the same length and breadth. If it is a vertical rectangle, this should also be a vertical rectangle with the same length and breadth. If this is a square, this should also be a square with the same side length. Is it understood? That is the very first thing which in the first look is going to help us detect whether the two matrices can even qualify to be equal or not. So, here when I am saying that length and breadth should be exactly the same, length of A should be equal to length of B, breadth of A should be equal to breadth of B, what I am trying to say is that the number of rows should be equal and the number of columns should also be equal. So, I am saying first condition is that M should be equal to R, that is number of rows in A is equal to number of rows in B. Okay. Next is N should be equal to S, that is number of columns in A should be equal to number of columns in B. Number of rows in A should be equal to number of rows in B, number of columns in A should be equal to number of columns in B. This is going to imply that the rectangular arrangement is exactly the same rectangle. That means the rectangle involved here or the rectangle involved here in matrix A is same as the rectangle involved here. The length and breadth of both the rectangles involved is the same. Rectangles involved means like over here, this is the rectangle that you can see if I complete it. Over here, this is the rectangle this that you can see. Over here, it is the square that you can see if I complete it. Right? In that sense, I am saying that every matrix A, every matrix B is associated with a rectangle or a square. Those rectangles should have the exact same dimensions. These are the first 2 points. Next, there is one more point. Just if the rectangles are looking to be the exact same or copies of each other does not actually mean that the two matrices will be equal. But yes, if these 2 points have been satisfied, you can still think that okay, these 2 matrices can be equal if the third condition is also satisfied. What is that third condition? Let's see. Over here, if you look at these 2 matrices, this is matrix A, this is matrix B. Now over here, if I talk about matrix A and matrix B, you can see this matrix has 3 rows and 2 columns. It is a 3 cross 2 matrix. This has 3 rows, 2 columns, so it is a 3 cross 2 matrix. You can clearly see length is the same, breadth is the same. Why? Because number of rows and number of columns is exactly the same. So the first condition, that is the number of rows in A is 3, which is equal to number of rows in B, right? Secondly, number of columns in A is 2, which is equal to the number of columns in B. Is it understood? Once this much is done, that means the rectangle is exactly identical. Third thing, let's see what is it. Now see, what is the advantage of having the same rows and same number of columns? Advantage is that 3 cross 2, if it is the order of both the matrices, the positions available in both the matrices will be exactly the same. There are 3 rows here, 2 columns, 3 rows, 2 columns, and therefore the intersections would be exactly the same. The identification of the elements would be exactly the same. Why? There will be a 1/1th element. There will be a 1/1th element of matrix A and a 1/1th element of matrix B. There will be a 1/2th element of matrix A and 1/2th element of matrix B. Why am I so sure? Because there are 3 rows and 2 columns. First row will be intersecting with both the columns to give you 2 intersections, 1/1th and 1/2th element, 1/1th and 1/2th element. Then second row will be intersecting with the 2 columns to give you 2/1th and 2/2th element. So there will be a 2/1th element in matrix A and 2/1th element in matrix B. Then the third row, and then also there will be 2/2th element here and 2/2th element here. Then the third row will be intersecting with both the columns to give you 3/1th element and 3/2th element. So there will be a 3/1th element here and a 3/1th element here, and there will be a 3/2th element here and also a 3/2th element here. So what I am trying to say is, whatever identifications are of the elements of matrix A, exactly same is the identification of the elements of matrix B. When I am talking about 2 matrices being equal, the matrices are known by the order and the elements. So order has come out to be the same. The moment order has come out to be the same, that means the positions available to both the matrices are exactly the same, and therefore there will be exactly same positions in both the matrices, and now we are concerned with the elements sitting in those positions. If the order is the same, that means positions are the same. At those positions, the elements which are sitting, the moment they come out to be the same, I say the matrices are exactly identical to each other, they are equal. So here, when the 1/1th element of matrix A and 1/1th element of matrix B become equal, I say that okay, I can proceed towards checking that the 2 matrices are equal or not. I basically want that each of the corresponding elements should be exactly the same. Why am I even able to make this fight? Because the positions available to both the matrices are exactly the same. If the positions would not have been the same, I would never have said that the elements sitting in those positions are same or not. But because the positions available in both the matrices are same, the next question will be that the elements sitting in those positions are same or not. Over here, matrix A's 1/1th element is 2 and matrix B's 1/1th element is also 2. This is the 1/1th element, A11, this is B11. Matrix A is 1/2th element, matrix B is 1/2th element. Matrix A is 1/2th element is 4, matrix B is 1/2th element is 1, and they are unequal. This is matrix A's 1/2th element and this is matrix A B's 1/2th. This is 2/1th. this is 2 1th element. Okay. Matrix A is 2 1th element, matrix B is 2 1th element. You can see both are 7. They are equal. Then matrix A is 2 2th element. This is matrix B is 2 2th element. This is 1, this is 7. They are unequal. Matrix A is 3 1th element, matrix B is 3 1th element. You can see they are both equal to 6. Matrix A is 3 2th element, matrix B is 3 2th element. This is 8, this is 8 and this is 0, and they are again unequal. What I am trying to say is orders were definitely same, and therefore the positions available in both the matrices were same, but the elements sitting in the corresponding positions were not all same, and therefore the matrices are not identical. Are you understanding? See, directly you cannot jump on the step of comparing elements same or not. Elements will be same provided you have a basis, a criteria to compare those elements. You will be comparing 1 1th element of one matrix with 1 1th element of another matrix, right? If 1 1th position is not there in the another matrix, how can you compare the elements of those matrices? So, to compare elements, you first need a basic criteria that only elements sitting at a certain position in one matrix can be compared to the element sitting at the same position in some other matrix, provided there is that position in both the matrices. And the positions will be same in two matrices only under one condition, one situation, that the orders are same. Orders are same implies the positions are same. Positions are same means we have the strong basis of criteria to compare the elements of the two matrices, because each and every position in one matrix is there in the other matrix as well. So, I can compare each element from this matrix with the element sitting at the same position in some other matrix, right. So, until and unless we have this strong criteria of having the same positions in both the matrices, we do not have the liberty to compare elements. Now, what happens is, if suppose I give you this matrix over here, let me just conclude that because what was happening is, matrix A's ijth element was not equal to matrix B's ijth element for every I and j, I varying from 1 to 3 because there are 3 rows in both the matrices, and j varying from 1 to 2 because there were 2 columns in both the matrices. Therefore, because ijth entry of matrix A and ijth entry of matrix B for every I and j is not same. For some I and j it is same. Like over here, for I equals 1, j equals 1, capital A's ijth element is equal to capital B's ijth element. That means capital A's 1 1th element is equal to capital B's 1 1th element, but there is an I and there is a j, there is I equals 1 and j equals 2, for which A ij, that means A's ijth element is not equal to B's ijth element. So, until and unless A's ijth element is equal to B's ijth element for every I and j, there are common I and j's available in both the matrices because the orders are same, so positions are same. So, whatever is the Aij's over here, same are the Bij's over here. The Ij's are not different. Therefore, corresponding Ij can be compared to the corresponding Ij. Exactly same Ij's are there. Until and unless each and every corresponding entry is not equal, I will not be declaring the two matrices to be the same. So, over here, as this is holding, this implies matrix A is not equal to matrix B. That is how you write it down. Matrix A is not equal to matrix B. Is it clear? So, now that I have explained it to you, let us quickly formalize this concept of equality of matrices. So, as I was saying, one thing I wanted to specify, I am saying that two matrices can be talked about being equal provided they have the exact same positions available. That means the orders are same. Now, see, you cannot say that, suppose I have 1, 2, 3, 4 and here I have 1, 1, 1, 2, 0, 1. You cannot say that this is the 1 1th element, this is also the 1 1th element of this matrix, and so they can be compared. This is the 1 2th element, this is the 1 2th element, So they too can be compared. There is no point of comparing these elements because there are positions different in the matrices. There is no 1/3 element over here, but there is a 1/3 element over here. There is no 2/3 element over here, but there is a 2/3 element over here. So don't get confused. I am talking about comparing elements of one matrix with another matrix, provided all the positions are exactly the same. All the positions. Fine, here there is no 1/3 position, but here there is no 2/3 position, here there is, and the difference is coming because of the orders being different. Orders create positions, positions come as a result of orders. Therefore, orders are different. This is 2 cross 2, this is 2 cross 3. So obviously there is one column extra over here, and therefore there are 2 positions extra over here, even when the number of rows is the same. Clear? So let's complete this article. So if these two are same, that means the number of rows in both the matrices are same, number of columns in both the matrices are same. That means what? If number of rows are same and number of columns are same, this implies positions in both the matrices, positions in both the matrices are same. The moment positions are the same, exactly same, the last step would be that the elements sitting in those positions have to be same. So elements, or I should write, okay, so elements of matrix A should be equal to the corresponding elements. Now I am not talking about the 1/1th element of matrix A being equal to the 2/2th element of matrix B. No. 1/1th element of matrix A will be compared to 1/1th element of matrix B. 1/2th element of matrix A will be compared to 1/2th element of matrix B. So corresponding elements have to be equal to the corresponding elements of B. Then we say A is equal to B. This is the notation used to imply the equality of two matrices A and B. Otherwise, A is not equal to B. This is another notation. Is it understood? The moment we have done this, let us deal with a question which is going to help us understand this concept even more. So the question is, find x, y, z provided, find x, find y, find z provided what happens? Matrix A, or let me not name it, it is x, y minus 1, z 0, 2, 1, 1, 5 is equal to 2 minus 1 minus 3, 7, 8, 0, 6, 1, 2. If these two matrices are equal, it's given to you, find the value of x, y and z. Is it even making sense? Yes, of course it's making sense, because the number of rows and number of columns over here is 3, number of rows and number of columns over here is 3. So the first and second condition have been specified. That means the number of positions, or whatever positions are there in this matrix, same are the positions over here. You can very easily see the rectangle is looking exactly the same. In fact, the rectangle is a square of side length 3. This is also a square of side length 3. This is also a square of side length 3. Now, once the square of side length 3, this is the exactly same, therefore positions available are same. If the matrices are given to be equal, that means the elements sitting in the respective corresponding positions are also same, isn't it? Over here what I can say is, this would actually be minus 1, this would be 0 and 2, and this would be 1 and this would be 5. Thus, you can see that this entry is the same 0, 2, 1, 1, 5, 1, 1, 5. If these two matrices are same, even these entries will be same. These are corresponding entries. Why? Because this is the 1 1th element of this matrix and this is the 1 1th element here. This is 1 2th element here, this is 1 2th element here, this is 2 1th element here and this is 2 1th element here. So, say this is matrix A, say this is matrix B. As A is equal to B, this implies matrix A's ijth element will be equal to matrix B's ijth element for every I and j varying from the 1 to the common number, because they have the same rows and same number of columns. This means if it is true for every ij, it is true for 1 1th, 1 2th and 2 1th. So, capital A's 1 1th element is equal to capital B's 1 1th element. Capital A's 1 2th element is equal to capital B's 1 2th element, and capital A's 2 1th element is equal to capital B's 2 1th element. This implies x is 2, this implies y is 1, and this implies z is 7. These are the values of x, y and z. We had to find x, y and z, which we have done. So, revise this concept nicely. I will see you in the next session. Thank you.